Hello student, my name is Subham Raj and today we will learn about Faraday's law, electromagnetic induction and some related topic. Okay, so let's start with electromagnetic induction. So here there is a coil we have. Okay, now here I have a bar magnet, north pole and south pole. Now if I move this bar magnet in this way, then magnetic field of this bar magnet, due to which there will be magnetic flux, because some magnetic field will pass through this cross sectional area. Okay, and so we know that magnetic flux is equal to B dot A. So there is a magnetic field here and the surface area A, and so the dot product of magnetic field and area is magnetic flux. So when I move this bar magnet, then the magnetic flux will change. Okay, so when we move this bar magnet, then we see that there is some current induced in this loop, or when we joined ammeter in this loop, then we see there is some deflection in ammeter. So that is the proof that there is a current. If I attach bulb in this loop, then bulb will glow. So the situation is, when we move this magnet, then there is some current here, there is some current will induce here. Okay, this phenomena is called electromagnetic induction, because we get electricity from magnetism. Okay, so this is the phenomena of electromagnetic induction. The phenomena says voltage induces in the loop of wire when we change magnetic flux. Okay, voltage, or we can say EMF, or we can say current, induces in loop of wire when we change magnetic flux in the cross sectional area of the loop of wire. So this is the phenomena. Electromagnetic induction is a phenomena where when voltage is induced by changing magnetic flux. Okay, there is some law here which explain this phenomena, that is called Faraday's law. Okay, so what is this Faraday's law? So Faraday's law, there's two laws in Faraday's law. One, it is same as this electromagnetic induction, that when we change magnetic flux in the loop of wire, then voltage will induce or current will induce. This is the first law of magnetic. This is the first law of Faraday's law. Okay, the second law is, it is about amount of EMF, amount of induced EMF. Okay, Faraday's law, Faraday's first law. So voltage induces in loop of wire by changing magnetic flux. Okay, And the second law is says it states that amount of voltage or amount of EMF, amount of induced EMF is the product of number of loop and rate of change of magnetic flux. So when we move this magnet, then magnetic flux will indeed change. But when I when I quickly move this magnet, when we increase the speed, when we increase the frequency of this repetition of this to and fro motion, then EMF, induced EMF will be larger, the current will become larger. Okay, so here induced EMF is directly proportional to number of loop, one loop, two loop, three loop. So how many turns you have in your coil? Okay, this is your coil and this is called solenoid. So how many turns in your solenoid or coil? It depends upon EMF depends upon number of loop. Okay, so here you can say that if one turns in your wire gives for example 5 volt, and you are moving your magnet, then it gives 5 volt, then if you double this turn, then you will get 10 volt. Okay, so only when you increase your turns, then you will get double or triple EMF, induced EMF. Here you can see that you are getting more and more EMF, that is actually proportional to energy. So you are getting more energy by increasing only turns. How is it possible? It is free energy? So no. So because according to conservation of energy, without input we can't get any output energy. So when you double the turn, then you will get more voltage, double voltage. But one more thing, that you have to push more harder than earlier. Okay, so this double voltage you are getting because of you are pushing more harder than earlier. So that's why it is the result. So everywhere conservation of energy is followed. Now and this EMF is directly proportional to rate of change of flux. Okay, there is a loop of wire, and here I have a bar magnet, and in 1 second if I oscillate this bar magnet in this way in 5 times. Okay, and now in 1 second if I double the frequency, if I oscillate it 10 times, then voltage will be double as earlier than earlier. Okay, so it is directly proportional to rate of change of flux. Okay, so how quickly you move your bar magnet? Here we have seen that when we move this bar magnet, then voltage will induce. Is it only one way to induce voltage in loop of wire? So no, there are 3 ways through which we can induce voltage in the loop of wire. So let's see. So the first way is move magnet. Okay, the other ways is move your loop of wire. Okay, when you move this wire, this loop of wire in this way, then in this situation magnetic field, magnetic flux will change as well. Okay, so we have to change only magnetic flux, and if I change magnetic flux, then voltage will induce. Either you move this magnet or this coil or any other way. You can also rotate this coil. Okay, so in this situation voltage will induce as well. Okay, now the third is um, change current in another loop of wire. How? Let's see. There is a two wire. Here I have a battery in this wire, a switch वगैरह and switch. Okay, and there is a coil. So when you switch off, when you switch on this loop of wire, then current will increase, and so current will increase, then it will create magnetic field. Okay, and this magnetic field will make here flux, and since this current is increasing, so magnetic field will also increase, and so the flux will increase, and hence there will be current in this wire. Okay, now let's talk about Lenz law. So first of all, from here we can say that our EMF is equal to N d phi by dt. Okay, but you may have seen that there is a minus sign here. Why is this minus sign here? So we explain this negative sign through Lenz law. So let's talk about Lenz law. What is this Lenz law? So here we understood that when we change magnetic flux, then there will be current in the wire. But what will be the direction of that current in the loop of wire? Let's see that. Here we have a loop of wire. Okay, this is your front part of wire loop, and this is your back part. Okay, now if I oscillate this bar magnet, or either move this oscillate this coil, then there will be current, but that current will in this direction or in this direction. So the direction of current is in this direction, in such direction. The direction of current will be in such direction, so that that current will create magnetic flux, will create flux, magnetic flux in this cross sectional area, and that cross sectional and that magnetic flux will oppose the external magnetic flux, the magnetic flux due to this bar magnet. Okay, let me write it. Induced EMF or current in such direction so that this current or EMF can opposes the change in magnetic flux. Change the external magnetic flux. Okay, external magnetic flux by creating ons on magnetic field or magnetic flux. Okay, so let me explain this situation. There is your magnet and there is your loop of wire. Okay, so the magnetic field of this bar magnet, some magnetic field line will pass through this cross sectional area of your loop of wire. Okay, and this is your north pole and south pole. If I move this bar magnet in this direction, then magnetic field, number of field line move magnet in left direction, then what will happen? Then number of field line will increase. Okay, so if number of field line will increase, then magnetic flux will also increase, because magnetic field into area. Okay, now the induced current in this loop of wire, the direction of induced current will be in such direction so that current will create magnetic field, and that magnetic field will make a magnetic flux, and that magnetic flux will oppose this magnetic flux, magnetic field due to this magnetic flux due to this magnetic field. Okay, so these magnetic field are the direction of this magnetic field in this way. Okay, so this loop of wire will make magnetic field in this direction, so that magnetic flux will become opposite, will become negative of magnetic flux due to this bar magnet. Okay, if I take area in this direction, okay, then magnetic field due to source, yeah, or we can say external, it will be positive. Okay, and this is the magnetic field of loop, so area is in this direction, so magnetic flux of loop will be negative, so it opposes their cause. Okay, now if magnetic field in this wire due to current either in this direction or in this direction, so magnetic field is in this direction, then current will be, so in which direction? So we can use right hand curl rule. Okay, so from there we can say that magnetic current will be in this direction. Okay, so in this way we find direction of current. So through Lenz law we understand that how our current opposes their source, who produces that current. It's okay, so that's why we put a negative sign here, because this induced EMF opposes their magnetic flux, rate of change of magnetic flux. Okay, so rate of change of magnetic flux, and this induced EMF is in opposite direction. Okay, motion of conductor or we can say motional EMF. When we move a rod, a conducting rod, in the region of magnetic field, then there will some EMF will induce in that rod. Okay, that EMF is called motional EMF. What I am saying that if here I have a um, here I have a conducting frame. Okay, and now I have another rod which is sliding over this frame. Now the length of this rod is L, and the distance of this rod from this conductor from here is X. Now the magnetic field is into the screen. Okay, and it is uniform, it is not changing with time. Now if I move this bar magnet, if I oscillate this oscillate this bar, sorry, I am saying bar magnet, if I oscillate this rod, then EMF will induce in this rod. Since this rod is in closed circuit, so the current will induce. Okay, so the EMF will induce, and if I divide EMF by resistance of this rod, then we will get current. Okay, so the EMF is equal to, again same formula, N d phi by dt, but at this time the number of loop is 1, so EMF will be d phi by dt. Phi is a magnetic flux, so phi will be B dot A, which is BA cos theta. The direction of cross sectional area of this closed loop is into the screen, and magnetic field is also in this direction, so the angle between them is 0, so cos theta will be 1. Now BA upon dt, this magnetic field is constant, so dA upon dt. And area, what about area? So area is your, now at L will not change, but when we move this rod in this way, then X will change. Okay, then X will change, and if movement of this if I move this rod with V speed, then this V will be equal to dx upon dt. Okay, so from here we can say that area is L into X at any moment, but this X will change. Okay, B d Lx by dt. L is constant, so dx upon dt, and this dx upon dt is equal to velocity of your rod. So EMF, induced EMF, will be BLV. Okay, so this is the induced EMF in your rod. Now let's do some question here. It is a PYQ of JEE Main. So the question is, so here I have a coil here, okay, and there is a bar magnet. So if the magnetic flux through this area is changing, and it is the relation between change in flux, the relation between flux and time is given in the question, 5t cube plus 4t square plus 2t minus 5. Now if the resistance of this coil is 5 ohm, then what will be the induced current? Then find the induced current at time 2 seconds. Okay, so we know that EMF is equal to d phi upon dt. So here if we differentiate this flux with time, then we can find EMF, and if I divide this EMF by resistance of this loop, then we will get current in this loop. So EMF will be equal to derivative of differentiation of this flux. It will be 15 t square plus 8t plus 2, and when we divide it by resistance, then we will get current. Resistance is 5 ohm, then it will be 3t square plus 8 upon 3t plus 2. Now current at 2 second. So 3 into a square of 2 is 4, 8 upon 3 into 4, sorry, 2, then plus 2. Now when you solve this, when you do this calculation, then you will get 78 upon 5 ampere, which is approximately 15 ampere. Okay. Now take next question from NEET. Okay, NEET previous year question. So now here there is a loop of wire we have, and magnetic field in this direction. The value of magnetic field is 0.025 Tesla. Okay, the radius of this loop of wire is decreasing. This loop is shrinking, and the rate of this shrinking is given here. We can say dr upon dt, which is 1 millimeter per second. Okay, now we have to find induced EMF in this loop at when r will be 2 centimeter. So this r is decreasing at this moment when r is 2 centimeter. At that moment, what will be the induced EMF? So let's do. EMF is equal to again d phi by dt. We have magnetic field which is not changing. So from magnetic flux, we will take out magnetic field, and here dA upon dt. Now the area of this loop, which is pi r square. So from pi r square we can take out pi. So there will be dr square by dt. Now b pi differentiation of r square will be 2r dr upon dt. From here we know magnetic field, we know the value of pi and 2, and we know dr upon dt. Okay, so we will put all this data, and at this time at this r we will use this value. Then we will get EMF when the radius is 2 centimeter. Okay, so that's for all. Thanks for watching this video.